Okay, you may recollect we were talking about partial response signaling. Basically, we had introduced the concept of duo-binary pulse shaping by saying that we would like to achieve the twin objectives of eliminating intersymbol interference while using minimum Nyquist bandwidth and also using a practical pulse shape. And by a practical pulse shape, we mean a pulse shape which is tolerant to timing errors, perturbation errors, right? Because we found that we could eliminate intersymbol interference by using minimum Nyquist bandwidth by using the so-called sync pulse. But that unfortunately is not a practical pulse shape because it is not tolerant to timing errors, right? Because a small timing error can cause a considerable reintroduction of intersymbol interference, which is undesirable. And what we said was, okay, what we can do is introduce some amount of intersymbol interference in a controlled manner ourselves. That's what the duo-binary pulse shaping does. Okay, if you recollect, we know, and that is what the Nyquist second criterion tells us to do. Although it doesn't say so in so many words, but basically what we are doing is introducing a controlled amount of intersymbol interference at the transmitter. You may recollect this was the pulse shape that we recommended in the duo-binary case, in which the spectrum is confined to the Nyquist bandwidth, but it's no longer a rectangular spectrum of the Nyquist shape kind. Therefore, it will exhibit intersymbol interference, right? And what we do have here is the pulse which is now sampled not at t equal to 0 but at t equal to t0 by 2, right? And if you transmit a sequence of such pulses every t0 seconds and you sample them every t0 seconds displaced by t02 from the center, what we will get is interference from immediately preceding pulse, right? Because the preceding pulse and the present pulse values will be identical. For example, these are pictures which I am repeating. I had shown you these last time also. Suppose you transmit a sequence of 2 ones, then this will be the previous pulse, this will be the next pulse. When I am sampling at k plus 1 t0, I get a contribution. I'm sampling here. I'm getting contribution not only from this pulse, but also from the previous pulse. And the two together add up to give me this peak over here, right? Which I am calling some value f0. So basically, this was a very first problem I gave you in the exam that show that the final pulse that you will get, the sample value at the sampling instance would be the sum of the present pulse, present sample and the present data and the previous data, right? This is just a one-line answer to the question. If you had understood this, then the first question was really very trivial. Similarly, if you transmit a 1 followed by a 0, this is the situation. At the sampling instant, you will get a 0 amplitude, right? So this is a preview of what we did last time. So xk at the kth sampling instant for the duo-binary pulse shape gets contribution from the present value of the symbol a sub k and the immediate past value of the symbol ak minus 1. This is the sample value that you will observe at the timing instant t equal to kt0 plus t0 by 2, right? So that's the reason why I thought that the first question probably should take a couple of minutes only, because it was kind of trivial. If you had understood it, but perhaps you didn't. It's all right. All right. Now, based on this, we could work out a decoding procedure, which we also discussed briefly last time. I didn't introduce the decoding from this point of view, but it is now obvious how we can carry out the decoding. For example, when I think this is what I told you last time, that if we receive xk to be equal to either f0, okay, we can get three possible values, right? Because ak and ak minus 1 each can take two possible values, 0 and 1, right? Xk can take three possible values. If f0 is plus 1, if you get f0, that means your current digit is 1. If you get minus f0, your current digit is 0, and if you get a 0, your current digit is no. We only say it is opposite of the previous one. We shouldn't say current digit, we said there is a transition. The current digit is decided by the fact that it has to be of the opposite polarity to the previously transmitted digits. Right? So this is the way we can carry out a decoding, and as you might have appreciated, this can lead to error propagation. Right? Particularly when you are making this kind of a decision. When the receipt value is 0 and your decision is that whatever was the previous decision, complement of that is the present decision. Right? This will lead to possible error propagation in the sense that if the previous decision was wrong, then the present decision also will be wrong, and this may continue for some time. Right? Which is not a very nice situation. Is it okay?
So shouldn't it be the other way around? Like if we know a transition, we know next. If we have a transition, and suppose we have, and we have the next one is 1. Or suppose we have a transition from 0 to 1, the next one is also 1. So if we get from minus f0, we go to 0, and so we have 0, 0, 1, and like according to this.
No, it doesn't matter what sequence you have. The point is that the presence of a 0 can only tell you this much, that whatever was the previous decision, you must complement that decision now. Right? Suppose because of noise that decision was wrong for whatever reason. Occasionally in any digital communication, all this discussion that we are doing right now is under the assumption that there is no noise. Eventually everything is to work in the presence of noise, and no matter how carefully you may design your system, there are bound to be errors now and then. We like them to be as small in number as possible. Right? But suppose such an error has taken place. Right? Now we would not like these errors to be correlated so that introduction of one error causes a sequence of errors after that. Right? Which is precisely what is going to happen in this kind of a situation.
Give an example and describe how exactly we mean by the sequence.
For example, suppose ak minus 1, you had decided wrongly it is 1 while it was actually 0. A 0 was transmitted. Suppose by a fluke of noise you make that mistake. Right? Now let's say the ak, the new value is it was 0, and let's say the new value is that you transmit is also 0, right? Because you could be transmitting anything, right? Then xk will turn out to be I should take a situation where it becomes 0. If ak minus 1 was 0, that means it was being transmitted as minus 1, right? So ak.
So it could be ak minus 2. This minus 1 value.
So you assume it to be something, okay, you assume it to be say minus.
So when you say minus 1, you mean it's a string of zeros? At least 2 zeros.
No, just let me take it later. I think I have got one here. Why don't I just use that? Look at this. Okay. This is what you are transmitting. These are the samples that you are getting, and this is what you are going to decode them as. Right? Now, because you are getting a value 0 here, right? You are saying that this one, this decoded digit has to be a 0 because the previous one was 1. But suppose the previous one was wrongly detected as 0 for whatever reason. Suppose at this point I had made a mistake, and instead of correctly detecting this as 1, I had detected it as 0, right? Due to whatever reason. At this point now, I'll make a wrong decision that it is a 1.
But we have a single error detection capability.
Yes, sir.
Error detection but not correction, right? We'll be able to say that there is an error, and sooner or later, but we can't correct it, right?
That was the same case in the previous line coding schemes also. I mean, you had said that there is single error detection.
That is true, but here, in addition to all that, we have the possibility of error propagation. That is one error causing another error.
But the chances are that you are going to detect, I mean,
Not
obviously.
necessarily. We may not detect it also.
So because if you
You see, that error detection capability is for a single error. If multiple errors occur, we may not be able to detect, because the rule may be still roughly followed. You see, there may be situations, odd situations, where you may be able to detect. There may be odd situations where you may not be. In fact, there will be more often the case when there is error propagation, you will not be able to detect always with surety that an error has occurred, because multiple errors have occurred now, right? Some of them can be mutually complementary in the sense that the net rule may be still followed, who knows, right? So anyway, we are not going to a detailed discussion of the error mechanism, but this point is fairly easy to appreciate, that error propagation will tend to occur, right? Okay. So what can we do about it? Lender suggested, Lender is a name that comes repeatedly again and again in the context of partial response signaling. He was a pioneer of this particular technique in the 1960s. Lender suggested the use of pre-coding. Okay, for this purpose. That is, before you start transmitting your data, at the binary level itself, at the logical level itself, you do certain very simple operations. In fact, one very simple operation, which consists of the following thing. Suppose your data sequence is AK, alright? That is some string A1, A2, AK, and so on, alright? You do, by pre-coding, a transformation of this data sequence, and this, at the moment I am taking this data sequence to be in the logical form, 0-1 form, not level form, but simply logical form, represented, each bit represented by its value either as 0 or as a 1. This is transformed to another binary sequence at the logical level, BK, such that the kth transform bit BK is equal to AK, the present input data bit, exclusive OR with the previously transmitted digit BK minus 1. Right? So B sub K is what you transmit now, which is the exclusive OR of the true value of the present bit A sub K and the previously transmitted bit B sub K minus 1. Alright?
What is of K is equal to 1?
Well, you will have to assume some value for Bk minus 1, which you can arbitrarily assume to be either 0 or 1. Right? It doesn't matter. You have to start somewhere. Now if you do this, let us see what happens. Let us remember that, okay, let's just try to, suppose AK is 0. What will happen to Bk? Bk will be Bk minus 1. Right? That is, whatever you transmitted in the previous time instant, you are transmitting the same bit now. What will be the sample value of the waveform that you get now? Xk? It will be the two things adding together, right? Remember?
It will be F0 or minus F0.
Right. it will be either both plus 1 or both minus 1, right? So it will be f naught or minus f naught. The value of xk now would be either f sub 0 or minus f sub 0. Is that okay? Clear to both of you? Clear to everybody here? Similarly, if ak is 1, bk is the complement of bk minus 1. Very good. And obviously xk value will turn out to be 0. So your decoding is very simple now. You decide, I think let me write it again. The decoding process will now consist of the following. Decide that ak equals 0 if xkt0, I'll just write xkt0, but although strictly I should write xkt0 plus t0 by 2, right, is equal to plus minus f sub o, and ak is equal to 1 excuse me, if xkt0 is 0. So the kth digit is now decided by looking at the kth sample value alone. There is no decision that a transition is to take place, right? We are able to explicitly determine the value of ak by just looking at the value of xk. So there is no question of error propagation now. Is it clear? So error propagation eliminated by such pre-coding. Okay? So very neat way of taking care of error propagation. In fact, this kind of technique is also used in some other digital modulation schemes, particularly phase shifting and things like that, which we'll see later. It's called differential encoding in that context, right? But we'll see about that, talk about that separately when the time comes. Any questions?
Can we have a PT which has same values at 0 and t naught instead of minus t naught by 2 and t naught by 2?
There are many other kinds of pulse shapes which we can have, and I'm going to motivate some of them now and talk about it. But I will not take an exhaustive discussion of this because I think there is only a limited amount of time we should spend on this topic and then go on to the next topic. But I'll give you enough food for thought, and you can probably design a lot of pulse shapes on your own, right? I'll just talk about them in a few minutes. Okay. Before doing that, let us summarize what we have achieved by dual binary pulse shaping. What have we achieved? First, we have obtained zero intersymbol interference, right? Provided we sample at midpoints of what I have called signaling instants, right? We have done this. Of course, this zero ISI has to be taken a bit carefully because it is not strictly zero. It is effectively eventually zero because we are able to decide correctly in spite of the fact that we have deliberately introduced some intersymbol interference, right? Secondly, our pulse shape is such that it uses minimum Nyquist bandwidth right? Minimum Nyquist can come in the brackets. Minimum possible bandwidth, which is the Nyquist bandwidth, and which is perturbation tolerant, right? Why is it perturbation tolerant? Because the spectrum decays smoothly rather than sharply at the edge of the Nyquist band. In fact, if you remember the expression for Pt, asymptotically it decays as 1 by t square, not 1 by t cube. 1 by t cube was for the raised cosine family with r equal to 1, right, which occupies twice the Nyquist bandwidth. So that's the rate of decay, asymptotic rate of decay. And finally, as before, we still have some single error detection capability, right? Single error detection is possible. Without pre-coding, we have the problem of error propagation, which we can easily avoid by using pre-coding of the kind that we just discussed, right? So this summarizes our discussion on dual binary. It seems to have all the nice features that we like it to have, except for one which you may remember, and that is it doesn't have a spectral null at DC, which is the only other feature we would have liked it to have, which it doesn't have. Now this is precisely the problem that Lender addressed himself to again, and came up with what he called a modified duobinary system. Which has practically all the nice features of the duobinary scheme that we have just discussed, and in addition it introduces a spectral null at omega equal to 0, right? Let us see how we go about doing this. Let me first take the mathematics of it, and then we'll look at the picture. So basically the motivation is that we would like to have the properties of the duobinary scheme repeated plus a spectral null at DC, right? Which is desirable. Now, let me motivate it like this. If you were to look at the duobinary pulse shape structure a bit carefully, you would notice that it is really a composite function. This pulse shape Pt is a composite pulse shape consisting of two Nyquist pulses, two sync pulses separated by t0 seconds. Remember that?
Yeah.
One of amplitude f0, not f0, it is amplitude is some 2f0 by pi or something, right? Whatever the amplitude, it doesn't matter. Both of the same amplitude, but displaced from each other by t0 seconds. Only the sampling instants are different, and chosen to be different. This in fact forms the basis of designing other pulse shapes in general, right? We could select a linear combination of such time shifted Nyquist pulses or sync pulses to construct other kinds of partial response signals, right? And that's the basic idea of also the modified duobinary system, as well as many other partial response systems which people suggested later, right? So let us therefore construct a pulse shape P prime T which has the desirable property of having a spectral null. And you also know what we should do to have spectral null. We have done that discussion before.
Average of that.
The area under the pulse should be 0, right? For example, in the Manchester coded scheme, right? Split phase coding scheme, line coding, right? So similarly, the motivation here is not to use rectangular pulses but to use sync pulses so as to limit yourself in bandwidth to the Nyquist band, but at the same time have the advantage of zero area, right? So I think now it's very easy to appreciate why he Lender defined a pulse shape P prime T in a manner that I'm just going to write here. Maybe I should write it. Okay. It takes two sync pulses, one located at minus T0, other located at plus T0, and subtracts them out. Of course, this is the pulse shape defined for which is centered at T equal to 0. For defining the pulse shape at T equal to 0, centered at T equal to 0, what he is taking is the difference between a sync pulse located at minus T0 and another at plus T0. Okay. If you were to do that, maybe we can do that later, and I can first show you what the pulse shape will look like. Right. Obviously, at T equal to 0, it will go through a 0, just like the Manchester coding goes through a transition in the middle of the pulse. Right. Only thing is, instead of a sharp transition like that, you have a gradual transition like that, right? Because you're subtracting two sync pulses, the difference is like that, right? And we would like it to be like this so that the spectrum is limited, bandwidth is limited. When we discuss Manchester coding, we were not worried about the total limitation, absolute limitation of bandwidth to within the Nyquist band, right? We were generally saying that the bandwidth should be small, but we are not restricted the fact that the bandwidth should be strictly within this interval, right? So this is the pulse shape P prime T, which I have just mathematically defined for you. If you were to plot it, this is what it will look like. It has a peak here at minus T0, a peak at plus T0, and a 0 value at 0. Okay. If you were to simplify this a bit mathematically, I'll show that picture again in a few minutes. This will turn out to be very similar to what we had for the duobinary case. That is, we have instead of a cosine function here, I have a sine function here, naturally because we are going through a 0 at T equal to 0, and the rest is all very similar, right? Amplitude is 2f0 by pi and everything else is same, right? And the asymptotic rate of decay is again T square. All those nice properties seem to be there. Obviously the bandwidth will be limited to Nyquist band. Is it obvious or not? Because each of these two components are limited to Nyquist band, f0 by 2, right? Both of them have a rectangular spectrum with bandwidth f0 by 2, but together the spectrum will be something different when you combine it. But whatever it is, it cannot spill outside the Nyquist band, right? Because outside the Nyquist band, both of them are 0. That is why we have chosen sync pulses to form other signals, other kinds of pulse shapes, because each of the sync pulse itself is limited to the Nyquist band. That's the motivation. That's a general technique that we can use to construct, in fact, a whole host of partial response signals. What we have discussed here are only the duobinary and the modified duobinary, but there can be many others you can construct, right? So this is the pulse shape. If you are to evaluate the spectrum, the Fourier transform of this, obviously it will be the rectangular spectrum multiplied by e to the power j omega t0 minus e to the power minus j omega t0, right? Because the first pulse is located at minus t0, right? And the other is at plus t0, right? So we get this, which simplifies to 2jt sine omega t naught into the rectangular function. Okay. Questions? If you have any problems, please speak out.
Can you explain that part? Like how is very obvious that the difference will be Nyquist?
Sure, why not? This pulse, sinc pulse, has a rectangular function as a Fourier transform, right? Which is this. This is the Fourier transform. What is this rectangular function has width of f naught by 2, right? Corresponding to f naught by 2, you have this sinc pulse. This sinc pulse is being defined for that bandwidth only. Similarly, this sinc pulse, and this is your resultant spectrum. In fact, isn't it obvious from here? After I have written it down, if it was not obvious otherwise, it should be obvious from here, because you're getting some sinusoidal function here as a function of omega multiplied by this rectangular function, right? So whatever spectrum you have, it is ultimately limited by this rectangular function, which is multiplying this function, right? But when you linearly combine two spectra, which each of them are separately limited to the Nyquist band, that is, they are zero outside the Nyquist band, no matter how you will linearly combine them, the resulting spectrum will also be confined, because Fourier transform is a linear transform, right? If it is zero outside the band, both of the other terms are zero individually, the sum will also be zero, right? Yes, please.
What is T in the P omega expression?
Oh, it should be T naught. Thank you. Any other question? And that's what it looks like if you were to plot. You have the sine omega t naught function confined to the Nyquist band, right? And you can see the nice spectral null that we wanted at f equal to 0. Okay? Can we have the discussion pointed this way? It will be nice so that everybody else also can participate in it.
So how does this T comes in the expression?
So where does the T come?
T naught ds won't come. In the P omega expression.
Okay, I'm sorry.
There should be
T
no
naught should be
T.
there
There
before
is no T in the expression.
you take the previous step.
Maybe I have made some mistake in some step. Okay, you're right. As of here, it's from here to here.
1 by f naught. The P prime omegas are the first step. It should be 1 by f naught.
You've taken the waveform as f naught times.
Yes, yes.
I think the T naught comes here itself, right? That is a mistake I made, right? The T naught comes here itself.
That's fine.
Okay, now let us see what kind of things are happening here in time domain. The moment we are using a linear combination of sinc pulses of this kind, we have certainly got a new pulse shape which is band limited to the Nyquist band. But how is it behaving? What kind of intersymbol interference is being introduced? Certainly something is being introduced, right? Suppose I decide to sample this pulse at t equal to t naught for the current decision. Then what I really get is a contribution
Second previous.
from a pulse which is removed from it by two symbol intervals, 2-bit intervals, right? So let me show this pictorially or derive it pictorially for you first. Let's write this p omega. Let's try to realize this function p prime omega. One practical realization would be something like this. Let me call it p double prime omega. So I'm talking of realization of p prime omega. Okay? And call it p double prime omega, which is slightly different from p prime omega in the following way. everything is same except that this function that I have written here is really e to the power minus j omega t0 times what I should have got here. I have ignored this function, this constant t0 in this.
That means p prime omega is not by itself realizing.
It requires a certain amount of delay for realizing, because
So how can you prove it that it's not realizing?
we don't have to prove it. Strictly speaking, it is not really realizable as such, because we have an infinite duration impulse response and things like that. But what I have got here is not that particular problem pointed out here, but a simple way of realizing it.
So why are you writing 1 minus e to the power minus 2j omega t? After taking the factor out, it's like
Basically, I have taken this expression and taken e to the power minus j omega t naught outside, right? And sorry, e to the power j omega t naught outside, you get this expression. This and this are related by that.
Shouldn't it plus?
you won't multiply it by e to the power j omega t
Double
naught.
prime.
When we realize it, we don't pay emphasis to that factor e to the power j omega t naught, what we have taken out.
Just a second, I made some mistake somewhere.
So this is a different thing. Right? Double prime.
Hmm?
This is a different thing here.
It is only delayed.
Yeah, but
It is different.
I would have liked this to come from this.
Then you
It is
have to-
coming. It's fine.
E to the power minus j omega t naught. How? How is it alright?
So because you take e to the power minus j omega t naught common, so you get e to the power j omega t naught minus e to the power
Then
minus
you
j
won't have
omega
this
t naught.
factor of e to the power minus j omega.
Then should have been plus j to the power.
This won't be there at all.
It's fine. It's fine. You have to divide
It's
by
fine.
2j, sir. And that's the reason.
Oh yes, you have to divide by 2j.
और क्या?
Okay, I'm sorry. I also got confused, but yes. You take this out, e to the power j omega t naught, and then multiply and divide by 2j, and that resulting expression will turn out to be e to the power minus j omega t naught. Right. So anyway, what is the reason why I wanted to come to this expression is if I were to picture this by a block diagram, I could do that very easily now. It was only for that convenience that I did this. So what you do is, look at this expression again, p prime omega, right? We want to realize p double prime omega as a filter, as a pulse shaping filter, such that the transfer function of the filter is this, right? Such that if I feed an impulse to it, the output pulse shape will have the spectrum, because the impulse has constant spectrum, alright? So if I feed my data impulses here as a sequence, alright, then this transfer function, you can I think see it easily, is realized by this.
Delay should have negative sign, sir. In the adder. So one of them should have negative sign, the delayed one.
Oh yes, this is, if this is plus, this signal here should be minus, because there is a subtraction sign. 1 minus e to the power minus j omega 2 omega t0 into this, right? So it was to bring this expression, the reason for bringing this expression to this form was to realize it by a block diagram of this kind, in a very straightforward way.
So this that function is channel.
No, this is still the overall pulse function that we're talking about, but it helps me to interpret what I'm doing. Basically from that point of view I have drawn this diagram. Okay? This, mind you, this xt here is the waveform that you are receiving just before you are sampling the waveform and taking your decision at the receiver, and this is what you're transmitting. So in between you have everything else, the transmitting pulse shaping filter, the channel, and the receiving filter. As before, that discussion, that picture remains the same. We are not changing that picture at the moment. So let the input data sequence be AK, which is being represented by a series of impulses over here. So what is it that you are going to get here? Let me call this, obviously here also I am going to get some impulse sequence, right? Except that it's going to be sum of two impulse sequences, one coming directly and the other coming through this delay. Let me call this CK, sigma CK delta T minus KT naught. Obviously, CK will be related to AK by AK minus AK minus 2. This is the key equation here. Just like we had discussed AK plus 1 earlier there, AK minus 1 earlier, we have this is the corresponding equation here. Successive symbols are not interfering. The symbols which are interfering are removed by two intervals. That was clear also by construction, right? And AK is, you can write it as CK plus AK minus 2. So let us see, based on this, what can we say, how we will carry out the decoding, right? Or whether or not it is possible from CK to come to AK. First of all, it is clear, I think before we even discuss that point, what we should appreciate is that these CKs which are transmitted after sampling will come back to us as CKs, right? Because what is the pulse shape that is being used for transmitting them? The sync pulse. Of course, finally, what we are really transmitting is not the sync pulse, because finally we are transmitting the net effect of all this. But if we now think of the fact that we are transmitting not AKs but CKs, then it will look to us as if CKs are being transmitted by sync pulses, right? And therefore, since the sync pulses satisfy the Nyquist first criterion, they will be received without intersymbol interference, right? Is it clear? So CKs will be able to observe at the receiver. When we sample this, every T naught seconds, except for this delay of 2 T naught that we have got over here, we will see samples which are precisely CKs. So our observed quantities at the receiver are going to be this symbol CKs. And what we would like to see is whether from CKs we can correctly decide what AKs were, which is our actual problem, the decoding problem. And that comes from this equation. Suppose we say we get CK equal to 1. Now, what can we say about AK? AK must be?
AK must be
1 AK has to be 1.
AK has to be 1.
the one, it has to be
So
Because it is.
so you are subtracting something from AK.
Is it obvious or not? Everybody says so, but not giving a correct, complete picture. Alright, let me proceed further and we'll come back to it if necessary. If CK is minus 1, AK must be 0. We are talking about AK as a binary entity here. Right. It is 0, 1 kind of thing. And the third possibility is that CK is, okay, I think I should have said this earlier. What is the number of levels of CK? Suppose AK takes 0 and 1 values. Once again we have 3 level system, right? Just like the dual binary system. So third possibility is CK is 0, when AK will be the same as AK minus 2. So that means AK is AK minus 2. So based on these two equations, let me rewrite it so that there is no problem. Our decoding strategy then becomes CK is equal to 1 implies AK is 1. It's equal to minus 1 implies AK is 0. ck equal to 0 implies that ak is equal to ak minus 2. These are the three possible values that you will receive, you will sample, and these are the corresponding decisions you have to take, right? And therefore a unique relationship exists between the sample values of ck and the decoded values of ak, except for the fact that once again there is a possibility of error propagation, because if you receive ck equal to 0, if you have made a wrong decision at k minus 2, you will perhaps again make a wrong decision, perhaps, not necessarily. Okay. So once again one can do pre-coding and things like that. In fact we'll come to that in a few minutes. At the moment let's proceed further.
What will be the pre-coding scheme now?
We'll come to pre-coding in a minute, but before I come to pre-coding, what I'd like to discuss with you is what have we achieved by doing all this. We achieved the spectral null that we wanted, but have we continued to achieve perturbation tolerance? Do you continue to have that property, perturbation tolerance? We'll have to look at the spectrum, right? The spectrum I already shown you. It has that half sinusoid shape within the Nyquist interval. It doesn't look like, it doesn't seem that it has a sharp cutoff, right? So therefore it must be perturbation tolerant. In fact, from the Pearl shape expression, it again becomes obvious that it is decaying at the rate of t square, 1 by t square, right, as t tends to infinity. So we now have a waveform which has the desirable features of introducing a control amount of intersymbol interference such that the data sequence can be decoded uniquely, plus it is perturbation tolerant, plus it is strictly limited to Nyquist band, right? So these two were remarkable achievements at that time in 1960s when Lender proposed the use of these for data communication, for effectively doubling the capacity of existing telephone trunks for data transmission, right? Existing cable trunks or digital trunks for data transmission overnight, by the use of dual binary scheme, one could double the transmission capability, isn't it? Because before that, before this concept of partial response signaling came into practical use, the only perturbation tolerant waveforms that were typically being used were the raised cosine family with r equal to 1, right? And that had twice the Nyquist bandwidth. So by just using a small modification of the waveform, by just doing a little bit of manipulation of the transmitter, we could now have a situation we could, for the same bandwidth, we could effectively double the transmission rate. We could have twice as many channels on the same cable system, which was a very remarkable pioneering achievement at that time in 1960s. Let's come now to the perturbation tolerant, the pre-coding aspect of this. You suggest to me what kind of pre-coding should be used here now. I think you can tell me.
XOR with the
Should be XOR with BK. BK is equal to AK with BK.
XOR with
Let me make a few inquiries. Okay, Nikhil, what is your opinion?
XOR with the not last one.
Let's say we want to create a sequence BK from the sequence AK, right? How should we go about it? It should be AK exclusive OR with
AK minus 2.
not AK minus 2.
BK minus 2.
So BK minus
BK minus 2.
BK minus 2.
Right, that's correct. Okay. Well, that's a good guess. I'm sure here they only guessed it. Because of the similarity of this equation with the previous one. See, what is the difference between dual binary case and this case? In the dual binary case, we had CK equal to AK plus AK minus 1 on the channel. This is what is happening on the channel. And in this case, we have AK minus 2. So because of this kind of index values that are coming into the picture here and index values coming into the picture here, it seems reasonable to try a pre-coding scheme of this type. Actually, there is a general theory of pre-coding from which you can take care of more general situations than this. But at the moment, it is sufficient to appreciate that this kind of pre-coding perhaps will serve our purpose. Let's see whether or not it will. So we'll use this sequence bk as the input to our modified dual binary system. What we'll be transmitting there is not a case but b case. But from the observed c case now, we'll be able to precisely decode the value of ak without referring back to previously transmitted pulse values, which is what we like. Let us see how. Your ck is now going to be equal to not ak minus 2 but b sub k minus b sub k minus 2, right? Which you can write as a sub k plus b sub k minus 2 minus k minus b sub k minus 2. Alright? Excuse me. Now, when AKs and BKs, if they we are assuming that AKs and BKs are binary symbols, 0 and 1 values, but this subtraction is not modulo. This is a real subtraction, right? That is the difference. So let us see what kind of decisions we can make now. Suppose CK is 1. What is the meaning?
AK is 1.
It implies AK is equal to 1, right? Because if CK is 1, that means BK must be 1 and BK minus 2 must be 0, right? Similarly, if it is minus 1, no, again it is 1. AK is still 1, right? Because when you see when how can AK be 1 CK be minus 1 when this is 0 and this is 1, right?
BK is 0.
So CK is minus 1. Now how can
BK be 0. Given BK2 minus is 1. That is only when AK is 0.
I'm sorry, I made some mistake.
It's fine.
No, this is fine, I know this is fine, but the argument, if AK is 1 and BK minus 2 is 0, we can have this as either plus 1 or minus 1. That is the question point, right? When
X0 should be 0, both should be 1. Both should be 1. BK minus 2 and AK should be equal to 1.
no. I always get confused at such points. Just a second. I think it is very simple. AK is
when AK and BK minus 2 are 1.
BK is 0.
When AK and BK minus 2 is 1. Or both are 1.
So we should do the reverse way, sir. So first we say if AK is equal to 0 and 1, then what happens?
Yeah, I think, okay, we'll start from there next time.